Hey YouTube, this is Arcus13 again, and double wired because I'm not sure that the battery device on these let me try that again. Double wired because I'm not sure the battery on these headphones can last all the way through recording, and for some reason, and wireless is not an option while it's charging. Don't know why. Now, I don't believe I've mentioned it yet on this channel, but I'm a huge fan of outer space. I mean, the whole reason I went to my first university was because it was one of the few schools that had an astronomy major. I mean, my brother got me a Lego model of the International Space Station for Christmas. That's actually pretty fun building it. Yeah. So, with the recent launch of the James Webb Space Telescope, I've decided to start a series about exoplanets and our own solar system. But first, let's provide a little bit of context. So, the James Webb Space Telescope is one of the most ambitious space missions ever planned. I've heard it said, and I've said this myself, that the James Webb is the successor to the Hubble. But it's more than that. While the Hubble was made to see in the whole visible spectrum, the James Webb was built to see in the red and infrared wavelengths. Development for the James Webb started in 1996, and the launch was originally planned for 2007. However, due to various factors, including design issues and the COVID-19 pandemic, it was pushed back until it was finally launched Christmas 2021. So, I could go on about the James Webb, but I don't want to distract from the point of this video. And there are plenty of other videos on YouTube about this, from both before, not even from well before it's ever launched. That's how long it's been. Yeah. Oh, by the way, this was also included with the ISS. And okay, something ridiculous about the International Space Station build. This is the size of the astronaut that is to scale, and this is a regular minifigure. Anyway, back to the script. So NASA hopes that the James Webb will be able to observe galaxies from almost the beginning of the universe. But more importantly for this video, they hope that the James Webb can study exoplanets. Now, you may be wondering, what is an exoplanet anyway? Well, basically, an exoplanet is a planet that orbits any star that isn't our own sun or Sol. Well, SOL if I'm not putting it up in this corner or this one, whichever. And so no planet that orbits a different star. That's literally all it means. But the reason why they are interesting is because they may provide a home for humanity's future, or they could be home to other intelligent species. So we've searched our solar system. There's nowhere else like Earth. Venus is too hot. Mars is too small. Maybe some moons of Jupiter and Saturn would work. Maybe they wouldn't. Our best chance lies beyond the sun's reach. Now, a reasonable question is, how can we detect exoplanets? There are three basic methods. The first is direct imaging. This is when we can actually see the planet through a telescope, such as the Hubble or the James Webb. This is very unlikely, since the light reflected off the planets would likely be drowned out by the light of the star. But there are very few cases where this has happened, and mostly get. Sorry, my cat. I was right next to the ISS model. I didn't want her knocking it off. Oh yeah. The cases where direct imaging has happened, like mostly like forming solar systems, although Proxima Centauri C, it was actually found like long before, actually found in a Hubble image long before Proxima B was even like confirmed as a planet. So that's an interesting story. But otherwise, it's not direct imaging is likely not going to happen. The second method is the Doppler method. Now this is going to get a little technical, so stay with me. First, what does the term Doppler mean in this case? Well, have you ever been standing like on a sidewalk and you hear an emergency vehicle coming with sirens blaring? The siren is like high pitched as it's approaching, and then it gets much deeper as it goes along. I did not mean to do that, but that is the Doppler effect. Whenever the source of a wave, be it sound waves or light waves, is moving, the waves become more compressed as it approaches the observer, and they stretch out as they travel farther from the observer. Or if I can find a good animation that my video editor will accept, I will include it. This is the basis of the Doppler method. If an exoplanet is large enough in comparison to its star, the star will move slightly as the planet orbits. The reason for this is complicated and is likely going to be the topic of another video. But as the star moves towards us, its light will be... Okay, I get that. I have that wrong. As it moves towards us, its light will be shifted towards the blue end of the spectrum, as that's the shorter wavelength. And as it moves away, let me try this again. As it moves towards us, it will be blue shifted as the wavelengths are compressed, and as it moves away, it will be red shifted as the wavelengths would be more stretched out. Now, if that red shift blue shift cycle occurs as a cycle, and a regular cycle, then that is a sign that there's a planet around that particular star. And the third method is the transit method. Now let me get let me get an appropriate model here. Okay, this may be blowing out the camera. It's certainly blowing out my eye, but let's say that this is the star. What? let's say that this is the star. Alright, like this is a planet going around it. As the planet passes in front of the star, or like as you can see, like it gets dimmer, or the less it's blowing out the camera a little bit less. I'm sure most of that is my finger, but that helps exaggerate the effect. In actuality, the effect would be very minor. Or it'd be like this. But if our detection instruments are okay, my eyes need to adjust from that. So okay, hold on. Let me get the mouse real quick. Okay, let's just continue with that with a wall. Like instead of the light bulb, let's just treat a face as a star. So, like as the planet passes in front of the star, or it will block out some the light as demonstrated earlier. And like plotting a graph of like the luminosity of the star over time, that was interesting. Oh, because so much of my face is in shadow. Okay. Plotting luminosity of the star over time, and we would see either we would be seeing a dip as these transits happen, and if they occur with a regular frequency, that is a good sign that there's a planet. Now, the Open Exoplanet Catalog says that the total number of planets, including ones from our solar system and unconfirmed exoplanets, is 4,732, and the total number of planetary systems is 3,516. This means, on average, each star system has 1.3 planets, and to me, this number seems suspiciously low. Let me explain why. And now I regret having found my cat's favorite toy in the middle of that last pause. Let's hope she doesn't make too big a racket. So let's use our own solar system as an example. As I will say in a future video, our solar system is an oddball. Now, let's say that there's a faraway alien species that's close enough to still be able to see our sun and our soul. Let's call all the species Bograni. Just maybe Bograni have Sirius is as the eye of a beast of burden. Who knows? Let's also say that their astronomy technology is as advanced as ours. And they'll and they'll be looking for habitable exoplanets as well. They'd scan a portion of the sky that includes a triple star system, with being the Alpha Centauri system, a white dwarf that orbits a blue giant, Sirius, and 2 yellow dwarfs, Procyon and Sol, amongst other stars. There may be several stars in their search field that they deem could have habitable exoplanets. Sol may not be one. Now, of course, we know that Sol can harbor life. That's our solar system. So why would they look elsewhere? Simple answer is they won't even see us. Yes. Looking at our solar system, the planet that would be easiest for a species like Bograni to detect would be Jupiter. Jupiter's radius is about 1/10 that of the Sun. She likes chasing it. Jupiter's radius is about 1/10 that of the Sun, and Jupiter is roughly 1/1000th the mass of the Sun. And it's massive enough and has a big enough diameter that Bograni would easily be able to detect the Doppler effect or transits if they were watching while the transits are occurring. The problem with our solar system is that Jupiter, or the planet most likely to be detected, takes 11.8 years to orbit the Sun. That means that Bograni would need to be studying us for at least that long to confirm the presence of Jupiter, or via transit. For reference, the Kepler telescope, which is the mission that has found the majority of the known exoplanets, was originally scheduled to have a 3.5-year service, and died after 9.5 years. According to the Open Exoplanet Catalog, the planet with the longest orbital period that we know of is Pluto, although planet is, and there is in quotes. After that, it's HR 8799c, with an orbital period between 215 and 240 years, although that was discovered through imaging a forming solar system.
Okay, so as I was editing this, I was looking back through the catalog, and it turns out that that is not actually it, because I noticed that planet B in that same system had a date. Planet B in that same system has an orbital period that they measured with like times 10 to the 5th, but for some reason the rest of the catalog doesn't quite. It does not realize what that means. So, it's not even planet B of that system. It is actually Fomalhaut B, which, if I explain what that is later, the system in the video, I will cut this part out. But Fomalhaut B is a planet and it is currently forming around its star. Yeah. Anyway, back to what I recorded about a month ago.
How did that stick go? There. The longest orbital period of a planet discovered by the Doppler method is between 57 and 260 years, which is a surprising range. Going by the transit method, DP Leo B has the longest year of 28 Earth years. But there's only two transiting planets that have periods that long, and the third longest in that method has a year of 10 Earth years. So what about the other planets? It's in our solar system. Well, Saturn, Uranus, and Neptune, and which are the other planets that would be most likely to be found, are even farther than Jupiter and have longer orbits, so they have a similar issue there. Granted, HR 8799c, it does have a longer year than Neptune, but as I said, it is still a forming planet. Mercury is a planet which is the shortest month, with the shortest orbital period of 3 months. Unfortunately, it has a radius that is 0.3% that of the sun's, and its mass is 1.6 times 10 to the negative 7 and times that the sun's mass. Which any redshift effect would be almost negligible. Well, especially compared to the giant planets. It's like Jupiter. And a Mercury transit would cause a light dip of only only 0.001%, although that is just my thought. It's like that because that's just how much surface area it would block out. I'm not sure whether or not it would actually be that much. Should have also calculated how much Jupiter would have. Okay. Now, so the fifth largest planet in our solar system is Earth. With a period of 1 year, that is more feasible for it to be found, but there are quite a few exoplanets that have most of the exoplanets we've found have periods of days or weeks.
And another mid-editing note: while looking at the in catalog, I was ordering it by orbital period. Earth is about an eighth of the way from the top, from the longest period. So that just goes to show how how do I put this? It goes to show that it is much more likely for us to find planets that have a shorter period than a year. Yeah.
Oh, yeah. Stick to the script, or else these brain farts won't happen. So Earth's radius is 0.9% that of the sun, and in Earth's mass, mass is 3 times 10 to the negative 6 times the mass of the sun. And so, while it would have a greater Doppler effect than Mercury, it would only have a light dip of 0.008%. And then add in the fact that Bograni would only be able to use the transit method if the plane of our solar system lines up with their home planet. It give or take enough margin of error, and they would really have a difficult time discovering us. So with all that in mind, I'd say the average number of planets is likely higher than 1.3. Optimistically, I say that it could be 5 planets per system, but a more reasonable estimate would likely be about 3 planets per system. But to get to the true average, human technology and search techniques will need to dramatically evolve. And that's it for this video. Be sure to come back for the next installment in this series. I'm not entirely sure what I will be discussing in that video, but I will still see you there. And yeah.